Hello and welcome to the free preview lecture series of my on-demand FE Electrical and Computer Exam Preparation course. In this lecture, we are going to go over cache memory within computer systems. Now, computer systems is one of those few intimidating topics for most of the electrical engineers who are taking this exam, primarily because they haven't taken any courses in their undergraduate coursework related to computer networks, computer systems, software engineering, and maybe sometimes even digital systems. So what I've done in my on-demand exam preparation course for FE Electrical and Computer Exam students is that I've added a lot of content in each one of these sections. So computer networks has upwards of 20 lectures, 25 lectures I believe within my course. Computer systems has upwards of 15 lectures. Software has more than 20 lectures. So even if you have no background in these topics, in these sections, knowledge areas, you can actually learn everything from scratch, at least for the context of the FE Electrical and Computer Exam. So cache memory when it comes to computer systems is a very important topic. You can look at the NCEES FE Reference Handbook, and they have dedicated a lot of real estate to cache memory. So that's why I have multiple lectures, and this is one of many lectures on the topic of cache memory. So let's get started. Hello and welcome to second lecture on the topic of cache memory, which is a subsection of computer systems. In this lecture, we are going to dig deeper into cache memory. We will start with a continuation of introduction of cache memory, wherein we will discuss the cache size and certain other aspect of cache memory. Then we will look into cache mapping techniques. We'll describe what cache mapping means, and briefly introduce direct mapping, fully associative mapping, and n-way set associative mapping. Then in this lecture, we will also take a deep dive into direct mapping, and the other two mapping techniques will be discussed in the next lecture. So as we discussed in the previous lecture, cache memory is divided into blocks or lines. Okay, this is how you can visualize cache memory. It will have a bunch of blocks. Okay. And the more generic term for these blocks is actually cache rows, right? Because we can have sets as well, which we will encounter in the next lecture actually. So these memory blocks can be of different sizes, as I explained previously. Okay, some can be 8 byte lengths, some can be 16 bytes, and so on and so forth. So the size of each block would vary depending on the type of cache memory that you're using. And the overall size of the cache memory, okay, is called the cache size. It is expressed in bytes, and it is equal to S times A times B. Okay, so for us to understand what S is, what A is, and what B is, let's look at the easiest one, the two easiest ones. The first one is let's say S, okay, the number of sets or cache rows. This is pretty simple. So you have these rows in cache memory. The total number of these cache rows will be one of the factors determining the overall size of the cache memory. Okay, let's say I have 10 cache rows. Okay, then you multiply it by the size, the block size. Okay, the size of each block. So each block is 8 bytes. Then your overall size of the cache would be 80 bytes. Okay, now there is this other parameter, which is associativity. Associativity determines the mapping technique basically, and we will discuss this in detail. For now, for simple illustration purposes and for comprehension, you can see that the greater the number of cache lines you have and the greater the size of each cache line, then the overall memory of the cache would actually be larger. And don't worry, we'll discuss associativity in detail when we look at each of these concepts. Generally speaking, a cache memory address is divided into 3 fields. okay, or 3 components or 3 segments, whatever you want to call it. So this is how a typical cache memory address would look like. Now, depending on the mapping technique that you're using, it can be slightly different, and we'll address that. But the first part is called the tag. Okay, these are the tag bits. This is the most significant bits. Okay, they appear on the leftmost side of the address. So they're the most significant bits, and they basically determine which main memory block is being mapped to the cache, okay, to the cache memory. So we bring data or instructions in from the main memory into cache. Okay, now tag basically gives us identification or some details about where in the main memory we are bringing the data from. Okay, index basically specifies the cache rows. Okay, so these can be sets or blocks. That's why I'm saying that let's keep it simple. Let's say that these are just rows for now. So it specifies the rows in which the main memory block is going to be copied. So if you're bringing some block in from the main memory, and whether it goes into block 0, block 1, block 2, or however many blocks you have in the cache memory, this one in particular has 128 blocks. So the index will basically tell us that which specific cache memory block this main memory block is going to. Okay, and block offset basically allows us to address or to locate individual bytes within the block. Okay, and this is the least significant bit of the address. Okay, by specifying whatever address you want to specify in here, you can actually reach a particular byte. Now byte is now this byte can, if you look at some other literature in NCEES reference handbook, they're using the smallest data size as byte, but more generically it can be words. Okay, and in some of the text you would sometimes see this as word bits. Okay, and the index bits are sometimes called as the block bits. Okay, because it specifies the block address, it specifies the set address, it specifies the row address. So the wording would be slightly different. Okay, the syntax could be slightly different, but the generic address is going to look like this. Cache mapping techniques. This lecture and the next lecture is all about cache mapping. So what is cache mapping? Cache mapping basically defines how a block is brought from main memory to the cache memory. Okay, so we have a secondary memory, let's say the hard disk, and when we bring memory from the secondary memory into the main memory, which is our DRAM, that is called virtual memory mapping. And now when we repeat the same process between the main memory and the cache memory, that is, we bring a memory block from the main memory to the cache memory, that is called the cache mapping. Now we know that the main memory contains equal size partitions, which are called memory blocks or memory frames. And during the process of mapping, some of the main memory blocks are copied to the cache memory. Okay, not all the blocks are copied. And the reason for that is that the main memory is much larger than the cache memory. Okay, and if you remember from the previous lecture, as the size of the memory goes up, the speed decreases. You may wonder, why not copy the entire main memory into the cache memory? Well, that's because the cache is not big enough. And if we start increasing that size of cache, then the speed would decrease, and that would defeat the entire purpose of having an intermediate memory between the CPU and the main memory. Okay, so we have to be strategic about what we bring in and how we bring in. And that basically means that the performance of cache memory mapping, how we basically bring in data or instructions from the main memory, is key to the overall speed. So if we can efficiently do this process, if we can have a high hit rate, if we can make sure that if we can anticipate whatever data CPU needs is available to it, then all of that will add up to increasing the overall speed of the processor. Cache mapping can be performed using these 3 techniques. The first one is the direct mapping, which we will discuss in detail in this lecture, and the next 2 will be discussed in the next lecture. So direct mapping is one of the techniques. The other technique is fully associative mapping, And the third technique is basically hybrid of direct mapping and fully associative mapping. It's called the n-way set associative mapping. Direct mapping. In the case of direct mapping, each main memory block that is brought from the main memory maps to exactly one specific cache memory block. Okay, it's very restrictive, it is very rigid, and we can only place a given memory block in a specific cache memory block. Okay, it is very simple cache mapping technique. It's very simple, and the issue with it, we will discuss the advantages and disadvantages later on, is that it is pretty rigid. Okay, and memory blocks are copied one at a time. That goes for all three mapping techniques: the fully associative mapping technique and n-way set associative memory technique as well. So we only bring one memory block at a time, but in the case of direct mapping, that one memory block can only go into one specific location within the cache memory. So this is a visual illustration of how direct mapping works. Okay, so you have main memory. As you can see, the size of the main memory is much bigger, and this is the cache memory. Okay, the size of cache memory is much smaller. So you can see that all the main memory blocks which are colored in red can only go to the cache memory block which is colored in red. Similarly, all the main memory blocks which are colored in blue can only go to blue memory block in cache. Okay, and the ones that are colored in red can go in red. The ones that are colored in green can go in green, or and so on and so forth. So mathematically, if the cache contains 2 raised to power n blocks, okay, and the data at main memory address I would be mapped as follows. Okay, so if we have 2 raised to power n, in this case you can see that we have 2 raised to power 2 because we have a total of 4 blocks in the cache. Okay, so the data at memory address I, so these are the memory addresses. Okay, 4, 5, 6. This is a very simplified version of how a memory block would look like, but the idea is that the cache memory block index for this particular main memory index can be given by this formula, where I is the address of the main memory address. Okay, and 2 raised to power n is the total number of blocks in the cache memory, and we take a mod, we do a mod operation, a modulo operation, which basically calculates the remainder. Okay, and that will give us the index in the cache block. Okay, so cache memory block number or cache memory block index is equal to main memory block number or main memory block index mod operation with the total number of cache memory blocks. This will make more sense when we do a couple of examples. So let's look at these examples. So let's say the main memory address or index is 0. Okay, so 0 mod 4 is equal to 0, because when you try and divide 0 with 4, the remainder itself would be 0. Okay, and when you try and divide 1 by 4, the remainder itself would be 1. Okay, and when you try and divide 2 by 4, the remainder itself, because 2 will not be fully divided by 4. Okay, so and when you divide 3 by 4, 3 will not be divided by 4, it will end up in the remainder. Now when you divide 4 by 4, 4 can divide by 4 completely. Okay, and the remainder will be equal to 0. All right, 5 won't get divided by 4 completely, so when you divide 5 by 4, it will result in a remainder of 1. When you divide 6, remainder 2, and so on and so forth. Now you can see a pattern developing here, right? So all the multiples of 4, including 0, okay, all the multiples of 4 will get divided by 4 completely, and the remainder would be 0. Now a value greater than a multiple, 1 greater than the multiple, will have a remainder of 1. So 13 will result in a remainder of 1. So 8 completely gets divided by 4, it is a multiple of 4. So 9 is 1 greater than 8, so the remainder will be 1. So the way it's going to work is that 0 will end up at memory location 0. So memory address 0 in the main memory will end up at memory address 0 in the cache memory. Similarly, 4 will end up at the memory location 0 because 4 mod 4 is equal to 0. Now 8 mod 4 is equal to 0 and 12 mod 4 is equal to 0 as well. So this is direct mapping. All of these memory blocks are restricted to a one specific location in the cache memory. Now how about 1 mod 4? 1 mod 4 is resulting in blue. It will end up in location 1. Similarly, 5 will end up in location 1. Similarly, 9 will end up in location 1. 13 will also end up in location 1. So you can see this pattern developing where certain memory addresses can go in certain locations only. And this is direct mapping. Now we will look into what happens when, so obviously one at a time, right? So if you've already copied 0 into cache memory, then 0, whatever was in the 0 block was sitting over here. Now you want to copy 4 from the main memory. Now in the case of direct mapping, we really don't have any replacement policy, or in other words, we have a replacement policy which is very simple, which basically says that overwrite, right? So if 0 was sitting here previously, the memory block 0 from the main memory was sitting here previously, we will just kick it out and we'll bring 4 in. And now if you want to copy 8, then we will kick 4 out and bring 8 in, and so on and so forth. Okay, at any given time, only one memory block can reside in cache at that particular location. But the idea is that we exactly know where each memory block in the main memory is going to go into cache. And that's what direct mapping is all about. So earlier we saw that equation where C was equal to S times A times B. Okay, in the case of direct mapping, so S is equal to number of sets, right? But in the case of direct mapping, the cache memory consists of blocks or lines. Okay, that's why the more generic term row is more appropriate, right? So S will be equal to the number of cache blocks, okay? And number of cache blocks are given by this 2 raised to power n, okay? Associativity is equal to 1. Now I'll explain this a little bit in detail over here. So associativity, and we will look at associativity in fully associative mapping and in n-way set associative mapping as well. So when associativity is equal to 1, it basically means that there is only one location where a memory address in the main memory can go to, from main memory can go to in the cache memory. Okay, that's why it's equal to 1. Now if it was equal to 2, then it would have meant that there are two possible locations where we can map a memory block from the main memory to the cache memory, and so on and so forth. Okay, and if this associativity is equal to the total number of blocks in cache, okay, this is very important. If this associativity is equal to the total number of blocks in the cache memory, then it basically means that we can map a given memory block from the main memory to any location, okay, to any location in the cache memory. And that is what will happen in the fully associative mapping. Now B is pretty simple. It's the block size in bytes. And we will make use of these parameters when we develop the memory address. So that's why I'm explaining them here. So let us consider a scenario. We have a cache memory which consists of 128 blocks. Okay, so the blocks will be numbered from 0 all the way to 127, which is 128. And each block contains 16 bytes. Okay, there are 16 bytes in each block. Okay, I don't think this is 16, but there will be 16 bytes in each block. So what is the total cache size? Okay, total cache size is so it is S times A times B. Okay, the same formula that we saw earlier. Now S is the number of sets or number of rows. In this case, this is the number of blocks. Okay, so the number of rows, we know that it is 128. And A, I explained previously, for direct mapping, A is always equal to 1. You don't have to worry about it. As soon as the question tells you that it is direct mapping, A will be equal to 1. So in this case, I haven't multiplied it by 1, but it's understood. and B is the size of each block, which is 16 bytes. Okay, so when I multiply these, I get the result 2048 bytes or 2k bytes. Okay, 2 kilobytes. That is the size of this cache. Now, what about our main memory? Now, if the question tells you that the main memory is addressable by 16-bit address, then it basically means that the size of the main memory is equal to 2 raised to power 16. Okay, so 2 raised to power 16 is 65536, which is 64k, okay, bytes. So there are, and each address is 1 byte. Okay, so each address is 1 byte. That is sort of assumed in here because we are dealing in bytes. It could be more generic, it could be words as well. So a 16-bit address would translate into 2 raised to power 16 memory locations, and each memory location is 1 byte. So you have 64k bytes. Okay, how many 16-byte blocks can exist in the main memory? Okay, now we are linking this together with the cache memory. So we have 64k bytes in total. And since the block size is 16 bytes, okay, block size is 16 bytes, how many 16-byte blocks are there in the main memory? It's pretty simple. It's simple math. So we simply divide 64k by 16 and we get 4k. So these are the total number of blocks in the main memory. So the main memory blocks will start from 0 and they will go all the way to 4k minus 1. So you can see that there are order of magnitude difference in the size of the main memory and the cache memory. So the cache memory goes from 0 to 127 only. It's much smaller than the main memory, which goes from 0 all the way to 4k minus 1. Now, if we are doing direct mapping, how will we map the main memory blocks to the cache memory? It's pretty simple. We just have to use that formula that I introduced previously. Okay, so cache memory block number, and that's what we're interested in. In which block will the main memory block go to, right? Which block of the cache memory the main memory block will go to. So we simply take the main memory block number and take a model, the mod operator, and take a mod with the total number of blocks in the cache memory. Okay, so let's do a few of these examples. So the main memory block 0, so this is 0 mod 128. 0 mod with anything will result in 0. Okay, 1 mod 128, 1 cannot be fully divided by 128, so it will end up in the remainder. 2 cannot be fully divided, so it will end up in the remainder. And 3 mod 128 will result in 3, and so on and so forth. So this will continue. Okay, this pattern will continue until we hit 128. 128 will fully get divided by 128 and the remainder will be 0. Okay, and then 129, the same pattern basically repeats. It will go until we hit 256. Now 256 gets completely divided by 128 because 2 times 128 is equal to 256. So it's a multiple. Okay, it's a multiple of 128. So this will be equal to 0 and this entire pattern will repeat again. Okay, so what you're seeing over here is that all the multiples of 128 will actually 0, and all the multiples of 128 will actually end up in memory location 0. Okay, so this is direct mapping, and everything which is 1 larger than the multiple, so 129, 257 and 513 and so on and so forth up until 4k minus 1, right? So you can calculate this up to the end of the memory, of the main memory. So these will end up, so everything that is resulting in a remainder of 1 will end up in block 1. Everything that is resulting in a remainder of 2 will end up in block 2. Everything that is resulting in remainder of 3 will end up in block 3. And this pattern will repeat until 127, after which it resets. Okay, so there are a bunch of blocks which will end up in the same locations, but one very specific location. Okay, and this is how we basically calculate which main memory block will end up in which location in the cache memory. Now that was mapping. Now we have to talk about the cache memory addressing itself. Okay, so we will develop on the same scenario that we have, that the cache size is equal to 128 blocks multiplied by 16 bytes. So you get 2k bytes. And in terms of the main memory, we have 4k blocks of 16 bytes. Okay, so the memory address, as I explained you previously, can be divided into 3 segments: the tag, the index, and the block offset. Okay, and we will calculate each one of these parameters or these descriptors or these bits for the cache memory address for the given scenario. So we know that the size of each block, both in the cache and the main memory, is equal to 16 bytes. We are concerned with the cache memory. Okay, so it's 16 bytes. 16 bytes is equal to 2 raised to power 4 bytes. So block offset bits, which are your least significant bits, these bits actually tell you the location of bits within each block. The length of these bits will be equal to log base 2 of the block size. So log base 2 of 16 is equal to 4. So if we have 4 bits in the block offset, we can actually access any byte within the block. Okay, because 2 raised to power 4, you can go from 000 all the way to 111. Okay, so you can access all 16 bytes within the block. Now the total number of rows in this cache memory is equal to the total number of blocks in the cache. Okay, now we are looking at the number of blocks. We know that the number of blocks is equal to 128, which is equal to 2 raised to power 7. So the index bits will help us determine which block we are trying to go to. Okay, so index bits is equal to log base 2 of s. In this case, s is equal to total number of blocks in the cache, which is equal to 128. So log base 2 of 128 is equal to 7. So if we have 7 bits in the index, we can actually access any one of these 128 blocks within the cache memory. And the tag bits will help us. So we can calculate the tag bits. First of all, we can calculate them by dividing the number of main memory blocks by the total number of cache memory blocks. Okay, so what does this tell you? So you have 4k main memory blocks and you have 128 cache memory blocks, and you result in 2 raised to power, so that gives you 32, 2 raised to power 5. So what it is telling us is that there are 32 blocks within the main memory which can go into one cache memory. So that's what the tag bit is telling us in the case of direct mapping. Okay, so you saw that 0 could be mapped to block 0, okay, because 0 mod 128 was 0. 128 could be mapped to block 0 because 128 gets divided by 128 completely with a remainder of 0. 256 could be, okay, 512 could be. So in total there are 32 such memory blocks in the main memory that can end up with one location. Same is true for block 1 because 1 mod 128 is 1, okay, 129 mod 128 is 1. So they will all end up in this location. So there are 32 such locations. There are 32 blocks in the main memory that can go in one block of the cache memory, and we can address them by using 5 bits. And this is the formula. Okay, this formula will change depending on what type of mapping you are using. So in the case of direct mapping, this is how we can calculate it. And number of tag bits would simply be equal to log base 2 of 2 raised to power 5, which is equal to 5 bits. So what is the advantage of direct mapping? As you can see, it is the simplest mapping technique. We really don't care about the replacement policy, and that's where the simplicity comes into play. Okay, so if you're bringing in a block from a main memory, just put it in the dedicated location, right? Block 0 in the main memory has a dedicated spot in the cache memory for it, which is block 0 of the cache memory. block 128 in the main memory has a dedicated location, although it coincides with the cache memory, but we can't care less because it's a very simple approach. And similarly, 256, if you're bringing in 256, you don't have to worry about whatever is sitting in block 0, just bring it over and we are going to push out whatever was previously sitting. So it's very simple, it doesn't require any replacement policy, and it is very easy to implement. So with all of that simplicity comes a few disadvantages. The first one is it is not flexible. So it is not flexible because let's say that the CPU is consistently requesting 0, 128, 256. So everything in the main memory which has a remainder of 0 when it is mod 128, right? So in that case, you can see that the remaining cache memory will stay empty and you are continuously just using one space. Although it's an extreme scenario, but for an argument purposes and for the sake of discussion, we can imagine such a scenario, right? So it results in inefficient usage of cache even when the cache is not full, because 0 mod 128 is equal to 0, 128 mod 128 is equal to 0, and 256 mod 128 is equal to 0. So even when we have the remaining cache completely empty, 99.9% of the cache is empty, you still have collisions, right? And these collisions will result in overriding and evictions. So poor performance if all three blocks are used frequently. Okay, so this will result in very poor performance. So it's simple, but it has its own limitations. So in this lecture, we digged deeper into cache memory. We looked into the cache memory address, we looked into cache memory sizing, and then we finally looked at cache mapping techniques. We briefly mentioned all three techniques, but we took a deep dive into the direct mapping, which is the simplest mapping technique. And in the next lectures, we are going to look into fully associative mapping and n-way set associative mapping. I did not want to overload this lecture with all three of these mapping techniques because we had to cover some ground in order to discuss mapping techniques themselves. So the structure of the address within the cache and some of the terminology. So that's why I dedicated this lecture to that prerequisite knowledge plus the discussion around direct mapping. For further practice, I'd recommend you to check out the quiz and also consider the study guide and practice exams for additional practice. Thank you. If you found this preview lecture helpful, I am confident that you will also greatly benefit from the full course that contains over 150 lectures and covers all the topics that are found in the latest NCEES FE Electrical and Computer Exam Specification. You will also get access to tons of quizzes and mini exams in this course that will help you get additional practice, along with a bonus full-length computer simulated practice exam. This streamlined and well-reviewed course comes with an amazing 30-day full refund policy, no questions asked. On top of all this, I have also included a special discount link in the text section of this video.